3 dimensions. So let's suppose we have our 3-dimensional plane here. And we have some random line, let's say here. And we'll call this L. And we have 2 points on this line. We'll call this P1 and just P naught. Now, because we're in 3 dimensions, we can represent any point as a vector. Okay, so we'll say vector, this vector going to from the origin to P1 is called R1. So this is vector R1. And same thing applies here. This is vector R0 or R0. Okay. Now we want it in the same direction. So we want the vectors going in the same direction. So we know how to do that, right? We actually did it earlier. So we have, there's a vector, call it here, that's perpendicular to both R1 and R0. We'll call that V. Right? We talked about that earlier. We can use a cross product as well to do that. Well, therefore, because it's perpendicular to this one and this one, it's parallel to the line we're actually looking for. That's the interesting part. And that's how we describe lines in 3 dimensions, or the equations of lines in 3 dimensions, is given 2 vectors itself, where we have an initial point, P0, and another point, P1 on the line, with a vector that's perpendicular or orthogonal to the actual one, gives us our line itself. So the vector equation of L1 looks like this, with T is a scalar multiple or scalar value itself. Now we're going to talk about something called parametric equations. So everybody's favorite. So don't worry, we're not going to get too crazy parametric equations until we get to later on in the course. But a parametric equation basically is we can represent the x and y and z component as different scalar multiples of the point. Okay. So what this means is give it a initial point, let's say P1, and its respective vector that's parallel to the direction we're looking for. So a parameterization of the equation looks like this in the x, y, z components. So both these describe line L up there in 2 different formats. So this is the actual equation of a line, and this is the parametric equations respectively individually. And again, we'll talk about what this means more importantly later on. But again, for now, why don't we do a couple examples so now we know how do we find equations of a line itself. So find the parametric equation of the line passing through 5, 1, 3, and parallel to the vector I, -7j, and k. And then find another point on this line. That's the key thing. So in other words, we want to find, let's say, like P1 up there. So we want parametric equations. So as long as everything's perfect, right? So we got the point, we have our initial point, and we have a vector that's parallel to what we're going for in the direction we want. So perfect. So every scenario is perfectly fine. So this is our vector. That's going to be our AB itself. And then our initial point is going to be that one there. So therefore we have x equaling, so the x component is equal to x, so 5 plus, and we go to a vector. So remember, this is A, B, and C respectively. So this is going to be 1t. We go to y. It's going to be y initial, so 1 plus -7t. And then finally z is going to be 3 plus 1t. And that's exactly our parameterization equation. Now that we want to find a line, a point on line itself, right? Another point, and you actually have, it's a line, so you have infinite points, and this is where it gets fun. So someone in the chat, give me a random number. Not too big. 5, perfect. So we're going to set t equal to 5. And we're just going to plug it into our parametric equations. So if I plug t equals 5, so 5 plus 5 is 10. Plug it in here. This is going to be 35. So 1 minus 35 is negative 34. And then plug in here, it gives you 8. There you go. That's another point on the line we have. Because t is some scalar, it really doesn't matter what you choose to be t. Because if our special case of t is 0, we get our initial point back. Right. So what if I gave it to you in a different format now? So find a parametric equation for the line passing through 5, 1, 3, so the same point above, and parallel, however, not to a vector, but to a line that's already parameterized to us. Okay. Now, unfortunately, according to our definition, I need an initial point, which is what we have, and I need a vector that's parallel to it. There's no other ends I could do so. Now, it says it's parallel, but it's parallel to a line, not a vector. But we could regenerate this vector given our scenario. Remember, by definition, our vector ABC is just the numbers in front of the t values. So therefore, this one, if I look over here, the vector we're actually going to be using that's parallel to this point is going to be 5, -9, and 1. Because those of them are in front of t. So we actually can do it. And again, now at this point, since we have it, we could just find the line. So x equals 5 plus 5t. Y is positive 1 minus 9t. And then z is 3 plus t. And there we go. Any questions there so far? Yep. All right. Let's do one more before we go on any further. Find a parametric equation for the line passing through 5, 0, 3 and perpendicular to both vectors I minus j and j plus k. So this is where it gets a little bit more confusing, where what am I actually doing? Because according to our definition, it's supposed to be parallel, but we want something perpendicular to it. Well, we just learned something that's perpendicular to it, so we know the cross product gives us something that's perpendicular to two vectors. So therefore, that's the vector we're going to be dealing with. So the vector that's parallel to what we want is the cross product of these two here. So we'll call this v and u vector there. So the cross product of v and u. So this is I, so that's 1, minus 1, and 0. This is 0, 1, and 1. So this is going to end up giving you negative 1, 1, 0, 1 I minus 1, 0, 0, 1 j plus 1, 0, negative 1, 1 k. So this ends up giving negative 1 I negative 1i minus 1j and plus 1k. And again, the key thing is, right, this is parallel to the plane, which is what we want. So this vector is parallel. That's good. And then now, using our point, we can find our parametric equations. So 5 minus t, 0 minus t, and then z is 3 plus t. There we go. Okay. Now we get into a little bit more theory. Okay. Now, the problem with when it comes to finding parametric equations of lines and lines in general is two things that are not good. The point and any parallel vector is not unique. They could change. Well, that's not good, right? So, how does it make it change all the time? So what that means is if I change the point or the vector, it will change both equations, right? So it changes both the parametric equations based off the point itself. So we call vector v something called the directional numbers of the line L. And by using the parametric equations, we have something called the systematic equations of L. And essentially all it is just solving for t. So basically we're just solving for t, and that gives us a symmetric equations of L. Okay. So this gives us uniformly, no matter what it is, what vector it is, and what point it is, gives us universal scale to deal with. Okay. So all of that we could do is, well, I can parameterize anything and just give it and create its symmetric equations based off that. And notice it's pretty straightforward. Again, given a vector and a point, instead of multiplying or being the front, we just divide it itself. It's pretty straightforward kind of stuff. So let's do an example so we can quickly do it. Find a parametric and systematic equations for the line that passes through the points 2, 5, 9, and -3, 1, 4. And the question now is something different. When does a line intersect the xz plane? Okay. All right. So first off, we have 2 points, so we got to find the vectors associated with it, right? So we need we'll say vector AB, because we need one particular vector. So this is going to be -3 minus 2, so -5. 1 minus 4, 1 minus 5 is -4. 4 minus 9 is -5. So that's our vector. Okay. So now you can pick any point you want. You could pick A or B. It really doesn't matter. I'll just pick A to be our initial point. And given our vector, so therefore our parametric equations are going to be 2 minus 5t. Y is equal to 5 minus 4t. And then z is equal to 9 minus 5t. And now using our symmetric equations, this is going to be equal to z minus 2 over -5 is equal to y minus 5 over -4. And this is equal to z minus 9 over -5. And again, what this makes is it forces the line to be the one particular line instead of like 2 random lines at the given points itself. Okay. And now we can actually solve for things like B. or the second part of it, is, well, what if we want to find a line of intersection, or what lines intersect this xz plane? Now, this is where, again, when I took this class, is like, what is it talking about itself? Is basically saying is, what if y equals 0? Because I'm only looking at the xz plane, meaning y is irrelevant. Well, if y is irrelevant, means y equals 0. And that means all I'm going to do is plug in y equals 0 into this equation and solve for x and z. And since it's a system of, well, not a system of equations, but universally scaling portion, I'm going to have x minus 2 over -5 is equal, plug in 0. I get 5 over 4. And same thing on the other side itself. And now all we're going to do is solve for x and z individually. So if I just cover this up, we can just solve for x there. So multiplying both sides by -5 is x minus 2 is equal to -25 over 4. And just adding 2 on the other side gives us the x component itself. So plus 2. So that's going to be essentially adding 8 over 4. And what does that give us? So 25 minus 8, that's 17. So -17 over 4. Y is 0, because we know that's it. And then solving the same thing on this side. So multiplying, so -25 over 4 is equal to z minus 9. And therefore, we just add it over. So 36, I believe. And that should give us 11. So 11 over 4. So when does it? It intersects at exactly that point there. Any questions there? Yeah. This side. So if I cover this up, you would just solve for z on this side. Z minus 9. So sorry, I did it here. So multiply both sides by -5 gives us this, and we just solve for z. And on this side, we could solve for x. Which is I did right here. Okay. All right. So last equation, I don't do too much, but it's pretty interesting one, is now if you're given two vectors themselves, how do you find the line segment? And it's that equation here. So given vector, so instead of giving points, you're given two vectors on the line, or two vectors that represent the line. Here's the equation for it itself. But most importantly now is what comes is how planes are created in 3 dimensions. All right. So a plane is basically a piece of paper in the XY plane. Now, just like we did for lines, a plane can represent it as vectors themselves. Okay? So let's suppose we have this vector R that touches this plane. at the very, at this point here. We'll call that vector r. And again, we have another point on that plane. We'll call that vector r now, our initial point. So we have initial point and another point on there. And we know that there's this line on the actual plane itself, and which you guys asked about this homework question, which is r naught minus r, right? The subtraction there. So we have a parallel line, or so a parallel vector. On this plane. And we can also find something that's perpendicular to it, going straight up from it. From this line here, or this vector here. Now, that's not the dot, the cross product, it's actually the normal vector, something orthogonal vector we talked about earlier. So this is perpendicular to that, going straight up, if you want to call it straight to you guys. So what we have is a parallel vector and a perpendicular vector that represents an actual plane in 3 dimensions. And that's exactly our equation for a plane in 3 dimensions, where n is our perpendicular vector, or our normal vector, and this is the vector that's parallel to it. Or in layman's terms, because we're always going to be dealing with the other kind of portions, we have something called the scalar equation, which is far easier to deal with. Okay, so our scalar equation for plane is given an initial point and a normal vector, and that's a key thing. It must be a normal vector. Here's our equation of a plane. Very similar to the equation of a line we had earlier. All right, so let's put this to practice. So find the equation of a plane through the point 2, 4, -1 with a normal vector n equaling 1, 2, and 3. And this is then find the intercepts of the plane. Okay. So pretty straightforward. Given n and a point, we can actually just copy this down. So our equation is going to be 1 times x minus our initial point of 2 plus 2 times y minus initial point of y plus 3 times z minus initial point of -1. That was hard. I'm joking. But that's pretty much it. That's what we did. Now you can distribute it. Sometimes your questions will may ask you to have to distribute and find what the end result is. But after a little bit of space, a little bit of time, I don't think you guys need me to do the whole distributing property and adding things together. I'll just give the end result. You see that. Right. And so let's go to part B. Find the intercepts of the plane. Now, again, this may look complicated, but remember, what does it mean by intercepts? Well, when is across the x, y, and z plane, or right, z axis? Well, let's just look for x, for instance. What's this point here on the x scale? Well, this is the point x, comma, 0, 0. Well, that's exactly what we're going to do now. Well, what if z is 0 and y is 0? What does x have to equal? So if we want, I'll just bring this to the other side. And if I let y and z to be 0, basically they're all gone, we get x equals 7. So our intercept for the x scale, x-axis, is 7, comma, 0, 0. And if we just do that all the way around, so now if I just, let x and z be 0 and solve for y, we have 2y is equal to 7. So therefore we get y is equal to 7/2. So this intercept is going to be 0, comma, 7/2, 0. And then finally doing the same thing for z. So letting x, y equal 0, solve for z, we get z is equal to 7/3. So my last point is 0, 0, 7/3. So that's where this plane crosses both the x, y, z axis. So it's kind of slanted. Right. More practice. Find the equation of the plane containing the 3 points 1, 1, 1, 2, 0, 0, and 1, 1, 0. All right. So this is what I mean by, you're going to have to not know your stuff, but remember what it means by the definition. Okay. Now, what I mean by the definition is, well, we have an initial point. We could pick any of the 3 points we want. It really doesn't matter which one you choose. However, we need a normal vector, no matter what. Okay, so remember, normal means we need something that's perpendicular to it. Okay. Well, we're given 3 points on this plane. So the first thing is we need 2 vectors that represent this plane. So we'll say this is A, B, and C. So we'll say vector A, B is this component, right? Subtraction. So when you subtract, you get 1, -1, -1. And do the same thing. We'll say AC. So this is my unit. So subtracting over, we should get 0, 0, -1. Okay. So now we want a vector that's normal to these two. And a vector that's normal to this means it's perpendicular. So therefore, our good old cross product comes into play. So before we go any further, we have to find the cross product of these 2 vectors. Yep. So this ends up being -1, 0, -1, -1, I, 1, 0, -1, -1, J, and then lastly 1, 0, -1, 0, K. Now you may think, oh, this is a lot of work, but the good news is these points are actually pretty nice because, right, you just get I, what do we get here? -1, that goes away, so positive J, and oh, that's even better. K is gone completely. So we just get the vector IK, or sorry, IJ, and 0K. Beautifully. So now we have our normal vector n. If you want, we could just put 0K just for practice. You can see it goes away, right? So now, given any point, I'll use just A for just because it's the first point. Now we could just plug it in like we did normally, which is right there at the very top. So remember, this is A, B, and C. So A, so be 1 times x minus 1 plus 1 times y minus 1 plus 0 times c minus 1 equals 0. So basically ends up being this. Or just x plus y equals 0. And there's our plane. And then I can ask you like the last question. This is very simple, right? The only thing that crosses is the origin 0, 0, the xyz plane. Yes. And that's a key thing, is because this is a 3-dimensional point, right? So we have 3 points that represent on the actual plane. So let's suppose we have this plane, we have this point, this point, this point. We can get 2 vectors like this, right? But according to our definition, in order to get the equation of this plane, we need something that's normal to it. And it's not enough just to get a normal vector, right? So we know what normal vectors are, the perpendicular to one particular vector. but this time we need a vector that's both perpendicular to both of them on the actual plane. So that's why the cross product comes into play, like you said. Yeah. So that's why the cross product is very useful to find these planes. Unless you're given it already. Because we're given it's normal to this plane as well already. And if not, we actually have to find it itself. Yeah. Any other questions? Okay. All right. This is a very interesting one. So linear equation of a plane. Okay. Now, just like you saw here, actually, let me look at this one. So I could find the actual normal vector just by looking at that. And we know what it is, right? It's given to us here. It's 1, 2, and 3. And notice that's 1, 2, and 3, meaning D has nothing to do with the actual normal vector we're looking for. Okay. What that means is now if you're given an equation of a plane like that, we can find its normal vector just by looking at the values in front of x, y, z only, because D is an arbitrary value of the line itself. So that's a very interesting fact there when it comes to it. Or that's another way of just solving for the equation of a line. Okay. But just for a little bit more practice, let's do 2 more to deal with it. And I think that's all we're going to be dealing with today, because I don't think I have time to finish up this section completely. So, example, find the equation of a plane containing the 3 points. So essentially, it's the same thing we did last time, right? So I just want to give you guys more practice on how to do this, just in case you're a little bit confused. So again, A, B, and C. So we'll say vector A, B, again, subtracting. Gives us that. And again, get the cross product. And just for the sake of time, I'm pretty sure you don't mind if I skip this kind of stuff. This gives you straight this. I hope you guys don't mind if I just skip give me that. And then we go straight to our equation, right? So again, I'll pick the first point because, it's just the first one there. So our equation would be -1 times x minus 1 minus 14 y minus 1, and then minus 4 times z minus 2 equals 0. And again, after distributing, you get this. Which is exactly our normal vector, right? So it's just another way to state it and see it from the actual plane. All right. This is the fun one. Find the point at which the line with parametric equations x, y, and z intersect the plane that. Oh boy, what in the world do we actually do here? Okay, so we have a plane. So we have a piece of paper. This is our plane here. Okay. We want to find the point where this other plane crosses it. Right, this line just goes right through it. Remember, this parametric equations is an equation of line. This is the plane itself. So basically, where does this point hit it? Right, where does this line hit this plane in 3 dimensions? Okay, and it's actually easier than you may think to do so, because all we're going to be doing is plugging x, y, and z into our plane. So in other words, I'm going to have 4 times the x component plus our y component plus 2 times our z component. And now we just distribute. All right, so collecting like terms, we get 7t minus 4 equals 10. So therefore, 7t is equal to 14. So we know t equals 2. Perfect. Now we have t equals 2. We could just plug it back into our parametric equations and find the exact point where it crosses. So I plug in t equaling 2 here. So -3 minus 2, -5. Plug in 2 over here. So that gives us, what's that? 18 plus 2 is 20. And then the z, plug in 2, 3 plus 2 is 5. So it crosses this point at -5, 20, 5. And this is what I mean by, where multivariate calculus gets pretty interesting, pretty complex,